All right, so today we're actually going to wrap up our function operations unit with a little talk on something called composite functions. This is going to be a little bit different than the ones that we've looked at so far. Remember, we looked at sum, difference, product, and quotients of functions, but composite functions are a little bit different. Anyway, let's get going. So again, like I said, we're going to finish off the chapter. We're going to introduce composite functions. We're going to create composite functions. Then we're going to evaluate composite functions, which means we'll plug in a number into them and then see what's going to be equal to. And then we'll identify the functions that created a composite function, which of course, you'll see what that means when we get there. Anyway, let's move on. So before we begin, recall the function operations we've covered so far. We've added, subtracted, multiplied, and divided functions. That's all the basic mathematical operations, right? I mean, some people could think maybe you could square root a function, but hey, we've actually already done that too. Remember, it was back in chapter 2, we talked about radical functions where you'd square root a whole thing, and then that basically made it so where the original function was 0 and where the original function was 1, those would be the points that stayed the same, and then between those 2 points are above it and then below it. It was a whole ordeal, right? So we've actually already square root functions. And then you could talk about, well, squaring functions, like taking it to a power 2, but that's really the same thing as multiplying functions as well. You're just multiplying the same function. So it looks like we've actually covered all of the operations, right? Well, let me just tell you, this ain't it, Chief, right? There's actually one more operation that we haven't quite done yet that we do need to cover. So here it is. So before we actually really define what a composite function is, I want you to recall back when we originally learned about horizontal translations. And hopefully you remember a horizontal translation is just something that happens just to the x, right? Not to the whole f of x, but just to the x part within the f of x. So if we had f of x was equal to x squared, if instead we had a horizontal translation to the right by 2 units, that would be f of x minus 2, which of course, in this case, because f of x is x squared, you just replace x with x minus 2. So it would become x minus 2 squared. So this right here kind of like acts as a replacement, right? So we're replacing what the input is inside of a function, which is changing how the function is going to look. Now let's suppose just x minus 2 was its own function. We'll call it g of x. So g of x is equal to x minus 2. Then this above translation could also be expressed as f of g of x. So it's like we took the function g of x, which is this guy right here, and we put that inside of another function. So we're taking the function of a function, right? So we took a function, put it inside of another function. Since the original function was x minus 2, like that's your g of x, and then you're putting that in f of x, which f of x is usually x squared, that means your input is actually the entire function g of x. So your input, instead of just being an x, would be your x minus 2. So again, this is like a function inside of a function. These are called composite functions. They're composed of more than one function. So one function serves as a replacement for the variable in another function. That's really important to understand. You're basically using an entire function to replace just the variable in your outsidemost function. So here's a bit of a visual of it. This visual is a little bit better if you're like literally plugging in a certain x. If you wanted to find what this was equal to when x is equal to 7 or something like that, you plug it into your innermost function. So you plug x into g, figure out what that's going to be, and then you take that answer and you plug it into f. So you kind of start on the inside and work your way out, as you would when you normally would have brackets, right? This one, it's kind of disappointing they didn't actually solve it, but I could give it a shot. It's f of g of x. G of x is x minus 5, and f of x is 2x plus 1. So that just means we take all of g of x, and we use that as a replacement for the input, or the variable, in f of x. So that would become 2, and then instead of x, you'd have to put in g of x, so 2x minus 5. And then plus 1, right? So g of x is replacing the x in f of x. So it's 2 times x minus 5 plus 1, which I guess if we were to expand that out, that'd be 2x, like by multiplying this through. And then 2 times minus 5 is minus 10, but then plus 1 makes it minus 9. So 2x minus 9, that would be f of g of x in that case. All right, we're going to do a lot more like this as well. Hopefully it's making sense. If it doesn't, hopefully it makes sense as we go along. So let's do a couple examples here. If f of x is 2x minus 2 and g of x equals x squared plus 3x, determine each of the following. Well, the first one here is f of g of x. So we're taking g of x and we're putting it inside of f of x, okay? So I guess earlier I said, oh, start with the innermost thing and work your way out. That's more if you were plugging in a number into here, like if we were trying to say like f of g of 5, for instance, so you're plugging in an x is 5. but we're not doing that in this case. So I'm going to have to kind of backpedal here and say oftentimes it's actually better to start on the outside and work your way in. Because what we're doing is, again, we're taking g of x, we're putting it into f of x. So we're using g of x to replace your variable. So I'll start by doing f of x here. So it's going to be 2 times x, but instead of x, notice our x has to be the entire g of x. So it's 2 times x squared plus 3x, and then minus 2. Now, it's always good to measure just to make sure that you are simplifying this and expanding it out as much as you can. So I'll multiply that 2 through. So this is going to equal 2x squared plus 2 times 3x is 6x, and then 2 times minus 2 is minus 4. So that right there, that would be f of g of x expressed in the best possible form. Now, what about g of f of x? So like this is the same idea, it's just g is the outermost function. So in this case, it's like we're taking f of x and we're putting it into g of x. This one's going to be a little bit worse because g of x has got an x squared there, but we got to just take care of it. So x squared, so instead of x, it's got to be the entire f of x. So it's going to be 2x minus 2 squared plus 3x, so plus 3 times 2x minus 2. So that's right. In this case, if you had actually 2 different x's in here, f of x has to replace all of those x's. Okay, so all of the inputs have to be replaced by your input f of x. Now we should really simplify this. The squared piece, like I mentioned before, is going to give us trouble. So we'll say it's 2x minus 2 times 2x minus 2 plus, I'm just going to bring the 3 into the brackets here, just for good measure for now. 3 times 2x is 6x. 3 times minus 2 is minus 6. Now I'll multiply these ones through. 2x times 2x is 4x squared. 2x times minus 2 is minus 4x. Minus 2 times 2x is another minus 4x. And then minus 2 times minus 2 is plus 4. And now I guess I can like break down the brackets here, because again, it's just an addition, so it's not going to do anything fancy here. It's just going to be plus 6x minus 6. Then I'll combine all my like terms here. For x squared, we only have the 4x squared, so we'll leave that as 4x squared. Minus 4x minus another 4x is minus 8x. And then minus 8x plus 6x is minus 2x. And then plus 4 minus 6, that's going to be minus 2. So right there, that is going to be our final answer. You don't have to factor it or anything like that. You can just leave it in expanded form. But there you go. That works quite well. Notice how those are definitely different functions. So f of g of x and g of f of x, those are not the same thing. You are going to get a different answer, at least most of the time you're going to get a different answer. So don't go thinking that they're the same thing. Anyway, moving on. All right, so if f of x equals 4 minus x and g of x equals x squared plus x, determine each of the following. F of g of 2. So in these kinds of questions where there's actually a number being put in as your ultimate here x, right? You don't actually have to make a function for f of g of x, for instance, because as we noticed, that's a little bit more work, right? So when I have questions like this, what I usually do is I say, all right, I'm going to evaluate the innermost thing first, g of 2, right? So if we're plugging 2 into this, that just means we have 2 squared plus 2, which is 4 plus 2, which is 6. So g of 2 is 6, okay? Now that leaves us with f of 6. So we're just plugging 6 into f of x now. So that's going to be 4 minus 6. Therefore, that's going to equal negative 2. So negative 2 would be our answer for f of g of 2. What about this one? G of f of negative 3. Well, it's the same kind of idea. Start with the innermost thing. We're going to evaluate what f of negative 3 is. Well, f of negative 3 is 4 minus negative 3. 4 minus negative 3 is positive 7. So that means this whole thing here, you know what, I can even just cross it and just say that's all 7. So now we're just finding g of 7. Well, g of 7 is going to be 7 squared plus 7. And 7 squared is 49 plus 7, that's going to be 56. So 56 is g of f of negative 3. All right, anyway, moving on. G of 1. This is the first time we've seen something like this. You can take a function of a function. Like you can put itself in itself. And don't think about it too hard quite yet, but we'll evaluate this one. G of 1 just basically just means evaluate g of 1 first. Well, g of 1 is going to be 1 squared plus 1, which is, of course, 2. So now we know we're just doing g of 2. G of 2 is going to be 2 squared plus 2, which is 4 plus 2, which is equal to 6, right? So there you go. Now here's a really wild one. G of 1, okay? You can actually stitch as many functions together as you want here. You don't just have to do 2 like we've been doing so far. You can do 3 or more, right? Like there's nothing wrong with that. It just makes it more work. When you're evaluating it like this, start with the innermost function. So g of 1, we actually have already determined that. We know g of 1 is equal to 2. And then that means we're taking g of 2, which we've also already determined in this last question. That's going to be 6. So you know what? I'm just going to cross this whole thing out. We're going to save us some trouble. We're really looking for g of 6. Well, g of 6 is going to be 6 squared plus 6. And 6 squared is 36 plus 6 is 42. So g of 1 is going to be 42 here. All right, moving on. All right, so another notation for this, and I'm not gonna lie, I hate this notation. I really don't like when people use this, but it will come around every now and then. You have to be prepared for it. The notation that I've been using so far, like f of g of x, that's my personal favorite because it makes it really clear what's going on. You're taking g of x and you're putting it into f of x. But another common way of expressing composite functions is this right here. F and then like a little open circle, g of x. How you read this is it's f of g of x, okay? When you read it like that, that's kind of like what I've already been saying, f of g of x. So it is the same thing, but just keep that in mind. This open circle here means you're doing a composite function. This is not to be confused with f dot g of x. If it's just a dot that's like a closed filled in little dot there, that means you're multiplying. It has to be f og of x, right? So just make sure you know the difference there. This notation is also very rarely used because that is quite confusing, but it does come around. So just keep in mind that those are different things. All right, we're gonna do a few more examples here. If f of x equals x minus 3 and g of x equals the square root of x, determine each of the following. Okay, so this is just us getting a little bit more used to that really dumb notation. Remember, just read this as f of g of x. So g of x is going into f of x. That means we're replacing any x in f of x with g of x. So this is going to become root x minus 3. Okay, that's all we had to do on that one. Now g of f of x, same idea, it's just in the other way around. That's saying that it's g of f of x, so f of x is going into g of x. So f of x is going into g of x there. That means this is going to equal the square root of, instead of x, we have to put in f of x, so the square root of x minus 3. So part C here, does order matter when composing functions? We've already talked about that. We've seen it firsthand. Yes, of course it does. Not literally always, though. There can be some very rare situations where the order didn't matter, but for like 99.9% of the times you're going to see it, order does matter, okay? Now state the domain of f of x, g of x, and the two composite functions. Well, we'll start with f of x. The domain of f of x, so in other words, the possible values of x we could plug in there, is x is an element of the real numbers. You can plug in whatever you want into there. There's not going to be any possible restrictions. G of x, on the other hand, remember, you can't take the square root of a negative number. So that tells us that for g of x, we have to say x needs to be greater than or equal to 0. No big deal there. Now let's talk about f og of x. I'm just going to like kind of use their notation here, even though I hate it. Once again, if you take a look at f of g of x, think about what x cannot be. Remember, x, or rather, you cannot take the square root of a negative number, so therefore x can't be a negative number. So once again, we actually have x is greater than or equal to 0. But here's going to be the really weird one. G of f of, ooh, what on earth am I doing? G of f of x, this one's going to be a little bit different. Remember what I said just a minute ago? You can't take the square root of a negative number, so x minus 3 cannot be negative. If it helps, you might want to write it out like this. X minus 3 must be greater than or equal to 0. This is no way to express a domain, though. We need to have our x all by itself. So let's just add 3 on both sides. It is an inequality, so you can do that. You treat inequalities just like you treat equations with a few extra rules. But that means it's x is greater than or equal to positive 3. So there you go. X is greater than or equal to positive 3. Because if you had, for instance, x was equal to 1, this would be 1 minus 3, which is the square root of negative 2, and that doesn't work. Okay? All right, moving on. Okay, so now we're going to use the example of f of x, which is the one in red, and g of x, which is the one in blue, to evaluate the following expressions. So this is actually a really creative way of solving composite functions. So even though we haven't actually composed these together, and we don't actually know what the composite function would be, like f of g of x, like we don't actually have a function for it, we don't even see its graph, you can use the graphs of the two individual functions to help you out here. Let's look at this one first, just to make sure the point's a little more clear. F of g of 1. Well, remember when we were evaluating it at a certain point, I always said, you know what, evaluate this piece first. So in other words, plug 1 into g of x and figure out what that's equal to. If you were to do this algebraically, you would literally just go, okay, plug in 1, so it's going to be 2 times 1, which is 2, minus 4, which is going to be negative 2. But you didn't actually have to evaluate it that way. You can literally just use your graph. G of 1 means when x is 1, what is y? Because g of x should be spitting out the y value. Well, when x is 1, which is right here, notice on the g of x graph, y is negative 2, as it should be, right? So then what we do is we're saying, all right, so it's negative 2 that's being plugged into f of x now. So really we're doing negative 2 squared, negative 2 squared, which is going to be positive 4. But keep in mind, you could also get that out of your graph as well. But how we have to do it this time is, notice in the first case, we were saying x is equal to 1, and then that gave us y of negative 2. It's that negative 2 now that needs to be plugged into f of x. So really, you're treating negative 2 no longer as if it's a y, but as if it was an x itself. So negative 2 being over here, if you look for what the y value would be, it's going to be positive 4. So either way you do it, whether you do it algebraically or if you do it graphically, the answer is still going to be 4 on this one, okay? I'll do this next one entirely graphically, because I don't think I really made that as clear as I should have. G of f of negative 2, okay? So doing this graphically means we need to figure out what f of negative 2 is. So when x is negative 2, notice y is positive 4, okay? So really we know this is g of 4. So now we have to evaluate g of 4. So looking at your graph, we can go 1, 2, 3, 4, and we can see that g of 4 is equal to 4, okay? So that one, I didn't even do anything algebraically at all. I just looked at the graph, and the graph was able to give me that information, which is really convenient if you know how to do it. I'll do this next one just graphically as well. No calculations, nothing. G of 3. All right, let's start with the innermost one first, though. G of 3. So when x is 3, y is going to be 2. So really, we know g of 3 is 2. So now we have to solve g of 2. Well, g of 2, if we look at where x is 2, we can see y is going to equal 0. So g of 3 is equal to 0. Hopefully that helped a little bit. Again, this is very convenient as long as you know what you're looking for. All right, I think this is the last thing we're doing here today now. Determine two functions, f of x and g of x, where h of x is f of g of x. So g of x is the innermost piece for the following problems. So we're given that h of x equals the square root of 3x minus 2. So basically, you have to think about what an outside function would be, as well as what an inside function would be. The outside function is going to be your f of x, and your inside function is going to be g of x. Let me help you out with this one. If we're thinking about what an outside overall influence of this function is going to be, I think a good guess to start with, and again, you can always guess and check this and see if it worked, but a good guess to start with would be our outside most function should be f of x equals the square root of x. Now, since this is going to be f of g of x, we have to think about what kind of g of x needs to replace this x. Well, the g of x that's going to need to replace that x is going to be this 3x minus 2. So I'll say g of x is just 3x minus 2. And if you ever want to check it, you can always say, all right, I'm going to take my g of x and put it into f of x. So that's going to be the square root of 3x minus 2, which is exactly what we started with. So this would be a valid answer. This one, however, a little bit more challenging. H of x equals x minus 4 squared plus 3x minus 4 plus 4. You probably are seeing what your input is on this one. Maybe you are, maybe you aren't. I'm not sure. But notice this x minus 4 is kind of a really big hint here. That's telling me that my input, the thing I'm actually plugging into this function, is that x minus 4. That's what I'm going to use to replace an x. And if you start thinking about it as what are you using to replace an x, that helps you make your f of x. So I can say that my f of x needs to be x squared, that counts for this whole piece, plus 3x, that counts for this whole piece, plus 4. So again, if you were to try this, plug in g of x into this f of x, you'll see it's x minus 4 squared plus 3 times x minus 4 plus 4. And that's exactly what we started with, so we know we're good there too. All right, so we're done. You definitely are going to want to get some practice at this. If some of the earlier questions are too easy for you, you might want to move on to some of these later ones. But page 507, questions 1 to 5, 7 to 9, 12, and 16. We had really decent amount of time today. We're only at about the 20-minute mark, so you have lots of time in your normal, regularly scheduled 36 minutes to get this done. And as always, if you need any help, please let me know.